sir, your slides are now visible. You may start with your lecture, please.
Sorry, guys. There was some problem with my internet, so I have restored the connection. Should I present from the beginning?
Yes, sir, I think your voice was distorted, so you may continue from the start.
Okay, thank you. My presentation is on molecular signatures, application of UV visible in FTIR spectroscopy. First, I have to introduce UV visible spectroscopy. UV radiation involves electronic excitations, uh, which is the difference in energy between the movement of electron from one orbital to another orbital. That is taking energy from 125 to 650 kilojoule per mole. The energy that correspond to electromagnetic radiation in the ultraviolet region is from 100 to 350 nanometer, while for the visible it is from 350 to 700. Somewhere you will find 800. So first I have to introduce UV visible spectroscopy. UV visible spectroscopy is an analytical technique used to measure the absorption of ultraviolet and visible light by substances. How UV visible spectroscopy works? Actually, when molecules absorb light at a specific wavelength, leading to electronic transition. So by this way, they lose photons, which we measure in the form
Excuse
of
me, sir. Sir,
yes,
your
please.
slides are not moving. Can you please switch them manually?
Okay.
Yes, it's fine now.
I have to share my whole screen because this will help share all my slides. Can you see right now?
No, sir, it's not visible. Yes,
Now?
yes, sir, it's fine.
Okay. So the basic principle was when electromagnetic radiation in the UV invisible region is absorbed by specific molecules uh, at a specific wavelength, they lead to electronic transition. The amount of light absorbed at each wavelength is recorded, producing an absorption spectra. By this way, we measure the UV visible spectra of that substance and we characterize that substance. Uh, the importance of UV visible spectroscopy in analytical chemistry is it is widely used for the qualitative and quantitative analysis for both organic and inorganic compounds. It is an essential tool for identifying molecular structures and functional groups. Uh, Actually, functional groups can be characterized by FTIR, but some part can be characterized here. Commonly applied in the fields such as pharmaceuticals, environmental monitoring, and material science. I have to tell you how it works. Uh, I have to bring a laser pointer here. Okay. Light absorption by molecules is taking place when electron transition, when electron jumps from one energy level to another energy level, from ground state to excited state. The specific wavelength absorbed correspond to the energy difference between these levels. So there are, you guys might know that there are three types of molecular orbitals. Orbitals, molecular orbitals, atomic orbitals, and anti-orbitals, where the transition of electrons is taking place by the absorption specific wavelengths. So there are four types of transition that is taking place during the electronic transition or UV visible spectroscopy. The first one is from sigma to sigma star, which are high energy, typically in the UV region. Then N to pi star, that is of moderate energy, that also occurs in the UV region. Pi to pi star transition, they are lower energy and can be both in UV and visible regions. Then the last one is N to pi star transition, that is having even lower energy, typically that occurs in the UV region. I have also listed that which compounds have these transitions, like for example, alkanes has pi to pi transition that is in the range 150 nanometer, sigma to pi star, sorry, okay, that's okay. These are other types of transition, but sometimes they are forbidden. That occurs in carbonyls, like it is taking, it happens in 170 nanometers. Pi to pi star transitions that take place in the unsaturated compounds from 118, it is around 180 nanometer, N to sigma star, that is in oxygen, nitrogen, and sulfur, or other heteroatoms like halogens. That takes place in 190 nanometer, and then carbonyls that takes place in the 300 nanometers. I have also given the energy difference between all these transitions, among which these four are among the common ones. Then I have to introduce what is spectrophotometer. So this is the schematic diagram of the spectrophotometer. The first one component is light source, which can be made of deuterium for UV, and it can be made from tungsten per visible range that has electronic, which has a range from 400 to 800 nanometers. And deuterium has range from 200 to 400 nanometers. That was for UV, and this one was for visible. The second component is monochromator. The function of the monochromator is it disperses light into its component wavelength, and it has various types like prism, diffraction, gratings, and the role of this component is it allow only to pass specific wavelength through your sample. Like for example, if you need 410 nanometer, so this monochromator will allow to separate the other colors and will only pass 410. Then another unit is key component is sample holder, or reference sample holder. So it usually a sample cavity made of glass or quartz. If it is made of quartz, it works for UV region, and if it is a glass, it works for visible region. And typically, its diameter length is 1 centimeter. It can be increased or decreased. Uh, then the last part is detector. That is photodiode or photomultiplier tube. That can be two types: photodiode or photomultiplier tubes. Uh, the function of this part of the spectrophotometer is it converts transmitted light into electrical signals, uh, and to measure the intensity of light that passes through the sample. There are two types of UV visible spectrometer. One is single beam, and the other one is double beam. Single beam has only sample where the incident light is passes through the sample and reaches the detector. And the double beam, we can also keep reference and the path of the double beam where the beam is divided into two beams with the help of a splitter. That's why it is called double beam, because the single beam that is coming outside the monochromator is divided into two double beams. So that's why it is called double beam spectrophotometer. Uh, the single beam measures the sample and reference sequentially, It is simpler. It is having simpler design but less accurate for changes over time, because first you have to keep the reference and then the samples, uh, and it takes also a lot of time to analyze your samples. On the other hand, double beam simultaneously measures samples and reference, so it requires small time. uh, it is more accurate and stable, compensates for fluctuation in light intensity. Okay, what type of samples will required for the UV visible spectroscopy, and how you will be analyzing them? Mostly, we use solution that is the most common, that is often in diluted form to an appropriate concentration, because there are certain limitations. UV visible spectrometer works in that limitation. You can also analyze solid samples that can be dissolved or dispersed in a solvent, so that will be once again in the form of solution. And sometimes you can analyze as a thin film if the light is passing through the sample. Uh, Gases can be also analyzed, but that required a special chamber. But it is very less common. That's why in practical, gases are mostly not analyzed with the UV visible. Uh, the most important, there are two parameters that is they are the most important, like path length and concentration. Actually, it is a Beer-Lambert law. uh, and the first one is the path length. Uh, Typically, 1 centimeter caveats are used, but other lengths are possible, as I mentioned earlier. The second one is concentration. If Beer-Lambert law is applied, where we say that absorbance is directly proportional to the concentration of the sample, and for the path length, we also say that absorption is directly proportional to the path length of the cell. So we are getting an equation: A is equal to epsilon CL, where E, like thing, is molar absorptivity, and A absorbance, C concentration, and then L is path length. Uh, you have also to remember, if you are using some certain solvents, so the solvents does have some impact on your lambda max. When you are selecting certain solvents, you must be that must be transparent, and you must know the range of that substances. There is a table, UV cutoffs you can find in various books. When you are using certain solvents, you have to use the cutoff values for your calculation of the lambda max, because the compounds can be identified with the lambda max. That is, I will describe in the coming slides. So this is one of the spectra from the UV visible spectrometer of this compound. This is the data output actually. The data output is the plot of absorbance versus wavelength. So here is the wavelength and here is the absorbance. Sorry, I haven't mentioned. There are certain characteristic peaks. You can see these are the peaks, and these correspond to specific electronic transitions for various groups. And the peak positions, so that is the lambda max, that indicates the wavelength at which maximum absorption occurs, through which we identify the substance. Like for example, in this case, for this compound, the lambda max is 206. There are other peaks also, like for example, this one at 252. This one is 252. This one is 206. That is the lambda max. This one is 252. This one is 317 around, and then 376. So this one is the lambda max of this compound, but you have to remember there will be other characteristics peaks along with this, through which you can identify whether this is this compound or not. The peak position depends on the molecular structure and the environment. So what environment you have provided, like the solvent, and the intensity of the peaks tells you that how much concentration of that specific part of molecule is present, and the shape of the peak also can provide information about molecular interaction and the sample environment. Where the lambda max wavelength of maximum absorption indicates specific chromopores. Chromopores are substances which absorb specific colors, functional groups that are responsible for absorption of colors, while absorbance value used to determine the concentration via Beer-Lambert law. And the band shape, if the band shape is broad, it can be also sharp band, which indicates different types of transitions and interactions. There are some important equations through which you can calculate transmission. Like transmission is emitted light versus divided by incident light. You can calculate percent transmittance, and by this way you can also calculate the absorbance, which is A is equal to log to the base 10 1 over T, and then you can correlate all these equations in the Beer-Lambert law. A is equal to ECL. Through UV visible spectrophotometry, you can do qualitative and quantitative analysis. That is the most important for researchers, because mostly people are working with nanoparticles or dye solutions in their labs, and they are determining the concentration of substances like dyes, like nanoparticles or whatever. Here is an example of rhodamine B dye at different concentrations. You can see 38 micromolar, 61 micromolar, 76 micromolar. And I have also given various cells having different concentration of a substance. Substance is unknown, but it is for to tell you how the light is passing through certain samples and how it can be affected with the concentration using Beer-Lambert law. Like for example, in the absorption 1, the light is passing from one corner to another corner. And the absorption 3, when the concentration is increased, so it can reach near the edge but cannot pass through the whole cell. And the other cell, it is passing only through half of the cell, and then it is blocking, so 100% of the light is absorbed. So that's why Beer-Lambert law, as I mentioned earlier, that absorption is directly proportional to the concentration. As you increase the concentration, the absorption will be increased. And there are certain limits up to which you can increase the concentration, because there is certain limitations of UV visible spectrophotometry. So you can also calculate of unknown substances. Like for example, if you don't know the concentration of, like for example, this middle one, the orange color, so you can rearrange the Beer-Lambert law like this: C is equal to A divided by EL, and you can calculate the concentration of unknown by using standard curve or calibration method, where you have to take certain samples in different concentration. Like for example, for rhodamine, you can take 30 ppm micromolar, 38 micromolar, 61, 76, 99, and 152 up to 152, and it gives you a linear relationship. And the linear relationship tells you the limit of that substance that can be determined. If this line is deviating from its line, so till then you can analyze your samples, otherwise you cannot. Okay, you can apply your the UV visible spectroscopic information for the analysis of organic compounds, that is qualitative analysis. You can identify functional groups like chromophores, that are groups that absorb UV visible light, example Gerasa, carbonyls, nitro groups, and aromatic groups. I have also given the list of these compounds and how these compounds, how these groups, how these chromophores are absorbing various types of wavelengths at various wavelengths. Like for example, alkene, there is an example, N-heptane. It is absorbing at 177 nanometer. We have also calculated the molar absorptivity and its transition type. You can also monitor the reaction type, reaction progress of your compounds. Like, for example, if you don't have NMR or mass spectrometer, you can analyze the progress of a reaction. So, like, for example, I have the example of pore nitrophenol. This is the spectra. This red one is the spectra for pore nitrophenol, and the other one is the spectra when it is added with sodium borohydride and it is reduced. So the spectra, the wavelength, the lambda max is shifting from lower wavelength to higher wavelength and lower energy. So this way you can monitor the progress. Like, for example, here the 4-nitrophenol that was reduced to with the help of sodium borohydride. So the lambda max has shifted. So this way you can know the reaction progress. You can also analyze various substances, organic compounds. Like, for example, here is the spectra for beta carotene that involves a conjugated system. So you can analyze for the conjugated system. Extended pi electron system shows characteristic absorption in the UV visible range. So one of the example is beta carotene, which have lambda max at around 450 nanometer. And you can determine this beta carotene in the food samples or other samples. You can also determine caffeine, you can determine other compounds. So we have some slides for that in the coming slides. Okay, this spectroscopy can also be used for the characterizations of various materials. Like, for example, it can be used for the analysis of semiconductors, like band gap measurement. We are using the absorption H in the UV spectra and a tau plot alpha HV whole square versus HV to determine the optical band gap. So this is one of the tau plot which we have run for a compound for the determination of band gap. You can also assess the purity and concentration of nanoparticles, like, for example, plasmon resonance for determination of gold nanoparticles, which can be determined at 20 nanometers. Sorry, I haven't inserted any example for this. You can find out on internet. You can also analyze dye-sensitized solar cells. Various types of work is on the way. Sorry, I have omitted various slides from this presentation because of the limitation of the time. That's why I was having some time, so that's why I have omitted some various slides. Okay, these are some of the case studies for various substances. Like, for example, the first one is for beta carotene. I already mentioned that it has a lambda max of 450 nanometers. Then caffeine, you can find out the lambda max, acetyl salicylic acid, aspirin, then acetone, and then you can also identify between naphthalene, anthracene, and tetracene, etc. You can also use this for determination of other complexes or organometallic substances, like, for example, trace 110 penanthroline iron 2, which has a specific orange-red complex color. This is the mechanism, how it is showing the color. UV visible spectroscopy has various advantages and limitations, among which some are listed here. The advantages of UV visible spectroscopy are it is highly sensitive, capable of detecting low concentration of enolates. It is having speed and efficiency, where rapid analysis with minimal sample preparation is carried out. It is a non-destructive techniques. Sample remains intact after analysis. You can recover the substance or the samples. Then after the second last is versatility, applicable to wide range of substances, including organic, inorganic compounds, nanoparticles, or materials. And you can also carry out qualitative and quantitative analysis, provides both types of analytical data. There are certain limitation associated with the UV visible spectroscopy. It has a range from 200 to 800 nanometers, and you cannot analyze beyond these ranges. There can be interferences with the UV visible spectrometer, or there can be sterilites or other absorbent species that can interfere. And it also requires transparent samples where light can pass through the samples. One of them is when you are analyzing the dyes or other substances, you must keep remember this thing that the solution is a bit transparent. The light can pass through the sample. If it is blocking all the light, you can analyze the sample. There is solvent effects, whereas solvents have various lambda max shifts. So you have to find out the cutoffs for those solvents. I have already listed the table. And the last one is the baseline noise. The instrumental noise and baseline drift can affect the low concentration measurement. If the concentration is very low, so the baseline will certainly affect the material. The next one is FTIR spectroscopy. So FTIR is after UV visible range, IR. And the first slide is about the introduction to Fourier transform infrared. It is a type of spectroscopy that is used in analytical chemistry to identify and quantify functional groups in molecular structures by measuring infrared light absorption. Basically, it measures, it determines qualitatively the presence of various functional groups in a compound. So the basic principle is molecules absorb infrared radiation at specific wavelength corresponding to their vibrational transitions. The techniques uses Fourier transform algorithms to convert raw data into a spectrum. So there is a difference between IR and FTIR, where in the FTIR, a Fourier transform algorithms that converts the raw data into spectrum from the IR data. So this is the most important you have to remember, because there is students are often confusing about IR and FTIR. And the importance of this technique is it is used for the structure elucidation, for the identifications of functional groups and molecular structure by analyzing characteristics absorption bands. You can also carry quantitative and qualitative analysis, and it can also be widely used in the fields such as pharmaceutical, polymers, environment analysis, and forensic science for determination of functional groups and molecular structures. Okay, how it works. Infrared absorption by molecules it is actually the vibrations of electrons when in the region of IR molecules absorb radiations, so that are taking their vibration is started. The vibrations are then two types, stretching and bending. So the first one is for stretching and then bending. There are various types like symmetrical, asymmetrical, twisting, rocking, wagging, scissoring. These are the types of vibrations. And this is the schematic diagram of an FTIR spectrophotometer. Actually, there is a difference between IR. So in the coming slide, I will show you what is the difference between IR spectrometer and FTIR. This one is the FTIR, where there is an IR source. When the light passes through beam splitter, it is going to the fixed mirrors where the lights is going up and down, and then they are Fourier transformed, and then after passing the detector, and the sample is the data is recorded. What is Fourier transformation? It converts the raw interferogram, so the spectra of the FTIR spectrometer is interferogram, that is called interferogram, that is converted into absorption spectrum using Fourier transform algorithms. So when that is Fourier transform algorithm, using their algorithms, So then it is called FTIR spectra. In the coming slide, I will show you how you can determine the FTIR spectra. So these are what type sources there are. And the FTIR spectra, there are four key components. One is IR source. So the IR source is typically a broadband infrared source such as Glover or less Nernest Glover. So that emits in the IR region. And then after that is the second component that is called interferometer. This one specifically is one of the type that is Michelson interferometer. There are other types of interferometers. So commonly used to modulate the infrared light and the interferograms by varying the path length of the infrared light. So this one is moved up and down, and with that the wavelengths are recorded. It has also a sample holder that is typically transmission cells for liquid, or ATR kit, attenuated total reflectance for solid samples or liquid samples. It can also be reflectance setup for solid substances. That will also be described in the coming slides. The last one is the detector. That is a common detector, include pyroelectric detectors or thermocouples. Then after, there are two types of FTIR spectrometers. The one is FTIR, dispersive FTIR, or you may also say that IR, that is just like the double beam spectrophotometer, where the sample and the reference cells are present, and there is no interferometer to convert the sample into FTIR spectra, while the other one is Fourier transform, where the Fourier transformation is carried out using interferometer to modulate the light, and then then perform Fourier transformation to obtain the spectrum. You can use three types of samples, three mechanism. One is transmission, that is used for the liquid samples, used as a standard specialized cells. The other one is attenuated total reflectance for solid, liquids, and minimal samples preparation. And the last one is reflectance, that is used only for the solid samples, especially those that are not easily dissolved. Okay, how to prepare your samples? For liquid, if someone is working, this slide is for those who are working with FTIR themselves. So for liquid samples, if you are using transmission cells, then cells made of materials like quartz or sodium chloride, the one we mentioned in spectrophotometer I showed you, it is just like those cells. Then how to prepare? Ensure the liquid is free of bubbles and particles, typically placed between two windows. So just like the view visible spectrometer, you have to remember that you have to make it free from the bubbles and other suspended particles. It should be clear and transparent. If it is, the sample is solid, then you can use the pellets. You have to mix that with the potassium bromide and press into a pellet for transmission analysis. If you are using an ATR kit, so you can directly analyze without extensive sample preparation. That is a very useful for powder and films. You have to put directly those substances over the ATR kit, and you can analyze directly. The last one is gases. For the gases, you have to use a gas cell. That is the specialized gas cells along with path lengths to ensure adequate absorption. To prepare the sample, you have to use appropriate gas handling techniques to ensure accuracy. The method is simple for transmission. The method is sample is placed between the two IR transparent windows, and the spectrum is obtained by measuring the transmitted light. If you are using ATR, the infrared beam is reflected within a crystal in contact with the sample, measuring the evanescence wavelength interaction with the sample. And you can also use diffuse reflectance or reflectance Here you have to put your sample to analyze the powder sample by light reflected using FTIR. Okay. Uh, Sample thickness and path length, that is like I mentioned before, the Beer-Lambert law. So that also works for the FTIR spectroscopy. The thickness should be optimized based on sample type and concentration to avoid structural and weak signals. So you can optimize this thickness, or you can consult with an expert of the FTIR who is using, if you have less amount of samples. The path length, that is also adjusted according to the specific requirement of the analysis method. So most of the methods, it is mentioned in the literature, are the one who is the operator of the FTIR will also let you know that what path length you have to keep in the sample. Okay, what data output you will be getting? So the data output of the FTIR sample is actually a graph, a plot between the transmittance versus wavelength absorbance. This is for the FTIR dispersion instrument. So that can be converted into intensities versus wave number. I will be telling you in the coming slides. So you can use this data for qualitative analysis for the determination of functional groups. Like uh, for example, if a compound present with OH group, so it will be between 3200 to 3600 per centimeter. Per carbon, it will be 1700 centimeter, and so on. There is a table in the coming slides for various substances where you can do qualitative analysis to determine the functional group or various types of compounds, what type of substances are present in your sample. You can also use the same material for quantitative analysis, where for this samples the Beer-Lambert law is applied. You can also prepare calibration curve like you prepared in the UV visible spectra, and you can measure the sample using various concentration, and the fixed intensities will let you know that how the concentration has decreased of the substance. You can apply the quantitative analysis for pharmaceuticals, environmental analysis, and material sciences. Uh, for quantitative pharmaceutical analysis, quantify active ingredients and drug formulation. You can also use for environmental analysis like measurement of pollutant concentration in air, water, or samples. You can analyze various types of materials, like, for example, polymers, nanomaterials, or other substances. And for quantitative analysis, it has certain limitation, like, for example, matrix effect, which is the interference from other components in the sample matrix that can affect accuracy, and the sample preparation methodology also impact the FTIR spectra. So you cannot determine then the quantity of the substance, because it will be giving you the wrong information. This is a graph of IR absorption range, where I have shown various groups that is absorbing in various regions. There is another chart of the same representation, where you have single bond to a hydrogen, that is stretching frequencies of the functional groups. So per OH, it is from 3600, it can be 3600, it can be from 3700 to 3000 to 3700 per centimeter. And for various types of OH, it can be alcohols, that is 3700. For free alcohols, it will be from 3600 to 3650 per centimeter. The peak can be medium or short. For hydrogen bonded OH, it will be 3200 to 3400, and for carboxylic acid, it will be 2500 to 3300 medium size intensity of the peak. Thus for amines, thiols, and other substances, you can measure from this table. So this is the table taken from Pavia book, uh, which is used for the characterization of various functional groups in the FTIR region. So you can apply the FTIR spectra for the determination of organic substances. Like I have already mentioned, you can determine for the alcohol that has a peak around 3600 to 3700 per carbonyls, that has peaks at 1700 per centimeter. Per amines, it will be from 1500 to 1650 per centimeter. You can elucidate the structure. You can also monitor the chemical reactions, because if has, let's suppose in the previous slide I have mentioned 4-nitrophenol that was having a hydroxyl group, and the other side that was when added with sodium borohydride, reduced with sodium borohydride, was having no hydroxyl groups. So you can monitor the reaction with that, with this type of spectroscopy also. You can also analyze the functional group in pharmaceutical compounds, that what functional groups are present or not. This way you can determine whether the substance is present in its original form or have degraded. So it can also be analyzed for the identification of polymers and other materials. Like for example, for the polymer analysis, determine the polymer types and their reduced by analyzing characteristic absorbance peaks. Like for example, polyethylene, polypropylene, based on their specific CH stretching frequencies, you can determine or differentiate between them. In the coming slide, you will see that I have shown a slide for polystyrene degradation, for which I have already worked myself. This is one of the case study for determination of functional biological system. This is the FTIR of biological system of DNA or RNA. So here, these two functional group is in the finger front region. So sorry guys, I have to mention that there are two regions. One is from 600 to 1600 per centimeter, that is finger front region, where the peaks appear very near to each other and they are very complex to analyze. And thereafter 1600 to 4000 per centimeter, that is a functional group region where the functional groups are present. So DNA and RNA, you can determine them in the finger front region, and the other substances, like for example water, lipids, and other substances, you can determine them in the functional group region. This is an IR spectra for alkanes. This is an example that how alkanes will appears, how the CH stretching will appears, and how the CH bending will appears in N-hexane, one of the example of alkanes. And thus for alkenes, then alkynes, then nitriles. So you can study these, and you can also study for alcohols, ketones, carboxylic acids, amines, etc. And you also can determine this for the amides. This is one of the spectra for gold nanoparticles. You can analyze gold nanoparticles where various characteristic peaks are present in the functional group region and finger front region. Both you can identify from gold nanoparticles. This is one of the spectra for the determination of a particular, and you can also check here, which has completely disappeared in this graph. With the increasing intensity, highlighting concentration of functional groups and compound. It is rapid for it is doing rapid analysis. It is also non-destructive range of applications suitable for a variety of fields, including chemistry, materials, and it most highly rapid analysis. You can use it for the qualitative analysis, It has also certain limitations, which include sample preparation requirements. So, like for example, some samples, especially solids, may require preparation such as grinding with KBR or using ATR. You have to use ATR, so that without ATR you cannot use it. You cannot use for the complex mixture. Like for example, analysis of complex mixture can be challenging due to overlapping absorbing bands. So that will have a lot of bands that will overlap each other. So you cannot analyze complex mixtures. You can analyze only pure compounds with this technique. You can also it is limited to IR active compounds. So only compounds with IR active vibrations are detectable. Those compounds which doesn't which are not active to IR vibrations, that cannot be determined. And resolution, and the final one is resolution and sensitivity. A lower resolution compared to some other spectroscopic techniques may affect detailed structure analysis. Thank you. So the forum is open for question and answer. You can ask the questions.
Assalamu alaikum, sir.
Walaikum salam.
Sir, I have a question from UV.
You have a question in UV.
Yes. Actually, sir, unsaturated compounds have the 150 nanometer lambda max around, but we have the D2 lamp only range 200 to 400 nm.
Can you speak
So,
louder?
D2 lamp, the range 200 to 400 nm.
Okay.
And also unsaturated compound is 150 nanometer wavelength around lambda max. So how we can analyze unsaturated compound with the help of UV?
You mean with UV in UV range, if
Yes, sir.
unsaturated compound have lambda max around 200 to 400, so you can analyze in the UV range.
Yes, sir. Because the unsaturated compound is around 150 nanometer, as we discussed in the starting, but also deuterium.
Let me tell you, like for example, here I got your point. You are saying that if you are using a deuterium lamp, so it has range from 200 to 400 nanometer.
Yes, sir.
So dear, unsaturated compounds have lambda max around 150 nanometers.
Yes, sir.
But if you are analyzing with the help of double beam spectrophotometer or single beam spectrophotometer using deuterium lamp, so you can analyze only from 200 to 400 nanometer. There will be no lambda max for that specific compounds. You can also, there is also other lamps that is can determine from 90 nanometer even to 400 nanometer, but most commonly that instruments are coming in the market that have a range from 200 to 400. For example, here we have mentioned that for the UV range, it is from 400 to 800. In my personal lab, I have a UV visible spectrophotometer, which has a range from 190 to 1100 nanometer that can even measure in the near IR region. So the lambda max for the unsaturated compounds will be in the 150 nanometer, but there will be other characteristic peaks also. You can identify that compounds from other characteristic peaks using deuterium lamp.
Okay, sir.
You got my
Sir,
point?
yes, sir. Sir, we are using quad cells for UV only and glass cells for visible. Why, sir?
This is because quartz cells doesn't absorb in the UV region, so that's why we are using quartz cells in the UV region, and glass cells that doesn't absorb in the visible region. And you are also baselining the instrument for the visible, for the solvents you are using. You are also using as a reference these compounds, so you can remove the wavelength of the glass in the visible region.
Okay, sir. Sir, what is the purpose of reference cell in double beam? Because we are
Actually,
because
sometimes it is also referred as matrix. Like for example, if you are analyzing your your substance, like for example, I have mentioned rhodamine B dye, and you prepared the solution in ethanol, let's suppose. So there are now two compounds in that one mixture, uh, rhodamine B dye dissolved in ethanol. So when we are when we are analyzing the rhodamine B in ethanol, so we have to keep the matrix of the ethanol of the solution. Like for example, ethanol in the reference cell, and then we will keep rhodamine dissolved in the ethanol in the other cell. So the ethanol in the cell will be the spectra of that thing will be minus from the max spectra of the rhodamine B. So that's why we are using double beam spectrophotometer. That's why the sample analysis with double beam spectrophotometer is very easy, faster than as compared to single beam. We are also using the reference cell in the single beam, but we have to keep first we have to keep the reference and then we have to keep the sample. So there are also a reference in the single beam, but that requires manual operation. While in the double beam, that doesn't require manual operation, but that will automatically minus that substance peaks from the sample peaks. You got it?
Yes, sir. Sir, I have
Thank you,
a
sir, for
question.
explaining the
Method
answer.
now.
Because most of the participants are
Can you
living in
ask?
India,
Hello?
so we
Sir,
will
Can you ask
provide some of the questions.
method?
Thank you.
methanol, sir, methanol cutoff is
Hello, Prof.
205.
Hello, Prof.
Yes, I'm listening to.
Yeah, I have a question. When we are running UV spectrophotometers and we want to determine the concentration of, let's suppose I want to determine the concentration of methylene blue after adsorption of these dyes on activated carbon. Now, let's suppose I put 100 ppm solution into the activated to the flask which containing activated carbons, and it absorb most of the methylene blue. And let's suppose at the end only 20 ppm solution remaining. So I want to determine this 20 ppm solution, which is unknown for me. Let's suppose now I put this into the vials of UVs into the cavette, and I put it into the in the UV spectrophotometers, and I pass the radiations. Now, when we pass this radiation, the absorbance will be automatically above of the two, because mostly for methylene blue, the absorbance range for 10 ppm solution is 2. Now we are doing dilutions because it is out of the range of these UVs. Now, normally we put like we take 1 ml of methylene blue solutions and then we put 1 ml of waters, and now it comes below 2, the absorbance. Now we are multiplied it by the dilution factors. My question is that these concentrations, if we do with our dilutions, and if we do it by the dilutions, the concentration will be same or will be different?
Sorry, I missed some points in your explanation. The one you are you were saying that let's suppose I'm measuring the concentration of methylene blue. You mentioned that. I'm
Yes,
clarifying the
yes,
question. Okay. Uh,
yes,
and after you have taken initially 100 ppm, and after the absorption it
let's
is
suppose,
now
sir,
20 ppm.
make it very easy. It is, let's have 20 ppm solutions. Now it is
Okay.
20 ppm is out of the range of the UV. Normally we will deal. Now I take 1 ml of this dye solution and I put 2 ml of water into this
Oh, okay, okay,
solutions.
I got it. Let's suppose
Yes,
there are two. I mentioned that there are certain limitations for UV visible spectroscopy. Like for example, here I have shown a standard curve calibration graph. If you say beyond the higher concentration, you can dilute it.
yes,
Definitely,
Professor.
you have to dilute it with ratios. If the concentration is lower from the
Yes,
limit,
yes,
Then there is another method that is used, that is called standard addition method.
Okay.
What we do, we are taking, let's suppose if you are taking 10 ppm, 20 ppm, 30 ppm, 40 ppm, and 50 ppm for your calibration graph, and that
Yes.
all of them are below the standard level, the detection limit. If they are below the detection limit, so what you will do, you will add a known amount of the dye to all of them. Like for example, you have to add 50 ppm of methylene blue to each of them, so it will be
Yes.
actually 60, then 50 plus 20, 70, and that will be within the limit. So by this way you can determine the calibration graph. You can draw the calibration graph again, and you can minus the standard that you have added to them. So then they
Okay.
will be in the limit. Okay, you got it?
Okay. Okay. And yes.
Assalamualaikum,
And
sir.
Professor, one another question.
Walaikum salam. Can you
Uh,
speak louder?
you hear me, sir? I'm here with you. I have another question.
Okay, okay.
Yeah, sorry, I will introduce myself first because sorry to say, I just want to confirm some things from you, and I really appreciate this course. Actually, this is my brothers who are attending this course, but when I see your slides and the methods you discuss with me, and I appreciate this course. And actually, this is neat for our youngsters because mostly our youngsters, they know to run the experiment because years we deal the students, we tell them how to run the experiment, how to synthesize activated carbons, but mostly they are unfamiliar with the instrument limitations, and the way of analyzing the samples. It's too much difficult for very difficult for them, particularly here in Pakistan, because we have a limitation of instrument and this type of things, and we are unable to do the sample again and again. But I really appreciate your this course. It's very good and very nice. But I one another, I just want to, like, not a questions, I just want to confirm. Normally the students doing this absorbance and UV, because in Pakistan mostly we using UV. Now there's mostly the student doing methylene blue 665 like this, and they use the same Caro, standard Caro, for even for the acidic pH and for the basic pH. So my question is that because of this pH, the lambda max shift, so automatically your concentration doesn't change, but your peak shift, and due to this you take the reading at 665 and you say, oh professor, my absorbance decreasing with the pH, so I select this pH, although it is only the shift, not maybe absorption. So I have the questions, are we have to work on the both regions, matlab acidic and basic standard Caro, or we have to work on the isobestic point like this? Hello, Prof.
Sorry,
Hello, Prof.
Uh, Please continue with the question. Otherwise, we should move towards the next question because we are running short of time. Is there any other question from the participants?
Yes, I have.
I have a question.
Please be short and concise. We are running short of time. It's already 12 p.m. So please shorten your question. You may ask now.
Okay, Assalamualaikum, sir. I want to ask that how IR is used for quantitative analysis.
Use FTIR for quantitative analysis. Mostly, FTIR is dispersive IR is used for quantitative analysis. You can also use the FTIR, the Fourier transform FTIR. The peak intensity can also show you that how much functional group of that substance is present there. So you can also use for quantitative analysis of substances for the same thing. So mostly dispersive IR used, and from dispersive IR data we still draw the calibration graph to Sadatullah, because it is the same mechanism mechanism for both of them. It also applies the Beer-Lambert law on FTIR spectra. So using
Yes, yes.
Beer-Lambert law, you can determine the substance concentration from the calibration curve method.
Sir, how beer Lambda applies on FTIR if we are using the solid materials for analysis?
Okay, this is actually Beer-Lambert law is for the solutions. If you are using solid samples, so there is again, I will mention that there is a Beer-Lambert law, like for example, the path length. So how much is the length of your solid sample? So if you are making it double, so the double absorption will be taking place. So still the Beer-Lambert law is applied to that.
Sir, we are using in the pharmaceutical industries. Uh, if we pour some samples around 10 mg or 20 mg, we have the same spectra as we have get. So how we can say that we can get the information about quantitative?
Which type of instrument you are using, if they are or disperse OER?
FTI here, sir.
I mentioned that mostly analysis.
Sir, because in the FTIR we are only detect the function
You
groups
got my
or
point?
bonds in the presence of our compounds. So we cannot get the point we can quantitative analysis performed by the FTIR.
I mentioned you that there are two types of FTIR, dispersive. That is just like the single beam or double beam spectrophotometer. The data that can be used for the quantitative analysis using Beer-Lambert law. If you are using Fourier transform, in some cases the peak position is changing with the peak intensity, but mostly it is not changing. So you cannot determine compounds per quantitative analysis. Fourier transform FTIR. You can use dispersive IR. And I have mentioned some certain limitations that is associated with the FTIR, among which one of them is the lower concentration. So, per lower concentration, you cannot determine how much peaks of that substance are present. So, you cannot do qualitative or quantitative analysis in that things.
Sir, I have a question also. If the
I think we
Sorry.
should, sir, I think we should end our session now. If any participant has another question, we can deliver it to you. I think it's the best option right now because it's already too late. So thank you everyone for participating, and thank you, sir, for your time and answering the question in detail and staying with us for your lecture and delivering a very brief and conceptual lecture. Thank you again. At the end, I extend my heartfelt gratitude to our esteemed speakers, Dr. Ashraf Ali, Professor Dr. Adnan, Dr. Fahmida Jabin, and Professor Dr. Nasimullah Qureshi. We extend our sincere thanks for your time, expertise, and dedication to share the knowledge. We are truly honored to have such distinguished speakers with us. There is an announcement regarding certificates of the workshop. So the certificates would be available on the website of IM Group of Researchers. I think they are uploaded right now, so you can visit our website to download your certificates. And thank you all the participants for being with us and your interest in knowledge and learning the characterization techniques. So hope to see you again at the same platform at another time. See you again. Take care and Allah Hafiz.